Hello, OCHEM 1 students. When we left off on Wednesday, we were looking at absolute configurations of chiral carbons, being able to distinguish between a right-handed and left-handed chiral carbon. To be clear, that distinction between right and left-handed is fairly arbitrary. We're looking at clockwise versus counterclockwise when we follow the Kahn-Ingold prelog rules. But I want to take an example where we know that we have a chiral carbon, but we aren't given any information about its chirality, and we want to project an absolute configuration onto it. So in this version of methamphetamine, we have a chiral carbon that is not shown as wedged or dashed, which means that this cannot be R or S as drawn. Remember, that's kind of like when I just sketched out my hand, but I gave no information about whether you're looking at fingerprints or fingernails, so you don't know whether this is R or S. It technically isn't either, or you can say that it's both. But let's say I wanted to change this so that I could show it as R or S. Okay, let's say I want this to be an S configuration. What I know about the S configuration is that the priority of the groups 1 to 2 to 3 will show up in a counterclockwise rotation. Well, because this is already drawn, I'm not really given a choice of how to arrange 1, 2, and 3. I have priority number 1 for my chiral carbon, the nitrogen, priority number 2, the carbon connected to a carbon, and priority number 3, the carbon connected to a hydrogen. Of course, my lowest priority is the hydrogen attached, and now this can be either wedged or dashed. You'll notice that my little sketch up here indicated 1 to 2 to 3 counterclockwise, but if I look at it where I have it, 1 to 2 to 3 is going to appear clockwise. That means that this will be an R configuration if we're following the rules and the hydrogen is a dashed group. If the hydrogen is dashed, fourth priority is going away, 1 to 2 to 3 takes on this clockwise rotation. I don't want it to be clockwise, but I can't change it to be counterclockwise. So what I can actually do is lean into that tip I gave you at the end of Wednesday's class. Make the fourth priority forward, which means we're breaking the rule and we're not looking at it from the direction we should be. We should be looking at it from the other side. When I look at that rotation from the other side, it becomes counterclockwise. That is an S configuration now that the hydrogen is going away. As it's drawn, it appears to rotate clockwise, but I'm breaking a rule, so it actually is an S configuration, in which case I want my nitrogen to be dashed. That means that it agrees with this. I want to be clear that if you're doing a problem like this and you're solving for the absolute configuration and you're not sure, or excuse me, you're attributing an absolute configuration and you're not sure whether you've actually got it right or not, let's say I wanted this to be S, I come in to analyze the priority of these groups, and I realize I'm following the rule correctly. My fourth priority is away, and 1 to 2 to 3 is an R configuration. That's not what I want. So if this is not the configuration I want, then I throw it out, and the simplest thing to do is to just swap the placement of those groups. Now I have my S configuration. What I did to make this structure from the one that I drew, hoping that it would be S, was I swapped the placement of H and N. I brought the hydrogen forward and I pushed the nitrogen backwards. I could have just as easily swapped the placement of the methyl and the phenyl groups. Now my priority groups 1 to 2 to 3 have actually flipped around. and I still obey the rule by having the fourth priority back. So remember, the difference between R and S is that any two groups swap their places. When any two groups swap their places, an R carbon becomes an S, or an S carbon becomes R. I do want to point out this is not something that molecules do on their own. They don't break apart their bonds, rearrange themselves in space, and reattach to a chiral center. This is a technique that we can use on paper when we're trying to represent chiral molecules and we want to represent them correctly. We have this trick of swapping these groups around. Okay, so I want to go through a couple of examples. Let's take the chiral carbon in vitamin C, and let's assign priorities 1 to 2 to 3. 1 through 4. From my chiral carbon, I have oxygen, carbon, carbon, and hydrogen. Well, it's easy for me to assign highest priority and lowest priority. From my carbon atoms, I'll need to start looking somewhere else. Here we have a carbon that is connected to an oxygen and then 2 hydrogens. Here I have a carbon that is also connected to oxygen and a carbon and a hydrogen. There's a hydrogen at this secondary carbon. So the carbons were not a point of difference from my chiral center. Those were the same. Both of those carbons were also bonded to oxygens, which means the oxygen bonded further along in that group is the same. But now I see a point of difference comparing a hydrogen to a carbon, and so I can assign priority 2 to the right, priority 3 to the left. As I assign rotation 1 to 2 to 3, I notice that it's counterclockwise, which means that it's going to appear S. But I'm breaking the rule about my perspective, which means that this is not an S configuration because I'm looking at it backwards. This is an R chiral carbon. When we move to limonene, things get a little bit trickier because I have less hetero atoms to start comparing against. So I find my chiral center and I look at the atoms attached. I have carbon, 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 and hydrogen. Well, my lowest priority is easy. The hydrogen there is the lowest priority. But between carbon, carbon, and carbon, I have no way of discerning a higher priority group. One trick that I can use is looking for degrees of substitution. A primary carbon will always be lower order, lower priority than a secondary carbon. As a primary carbon has less other carbons connected, a secondary carbon has more, a tertiary carbon has more than a secondary, a quaternary carbon has more than a tertiary. But unfortunately, I'm looking at a secondary, and a carbon that we don't typically assign degrees of substitution to. Because it's an alkene carbon, it's harder to decide whether it's tertiary or quaternary. So this, again, challenges because I have 2 secondary carbons. So let's go through and list out what these groups are bonded to. Here I have a carbon, which further down the line is connected to a carbon, and it also has 2 hydrogens. I have the same thing on the other side. I have a carbon connected to a carbon and 2 hydrogens down the line. On top, I have a carbon, which is very clearly connected to a carbon on the right and a carbon on the left, but I can count this double bond twice. Any double bond, that includes carbon-oxygen double bonds, carbon-nitrogen double bonds, triple bonds, they can count more than once as a connection to another atom. So this is 3 bonds to carbon that this carbon up top has. So as I look for a point of difference, I see carbon, carbon, carbon versus hydrogen and carbon. That helps me assign the group to the top as priority number 1. Now I go back to my other two groups, hydrogen, 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 hydrogen. These are not points of difference in the ring at all. So I move down to the next group on both carbons. Here again, I have a bond to a carbon and a bond to two hydrogens. On the left, I have a bond to a carbon, another bond to a carbon, and then one bond to a hydrogen. So as I look for a point of difference, carbon remains the same, but I compare carbon against hydrogen. Higher point of difference, higher atomic mass at the first point of difference. This gives me priority group 2 to the left, priority 3 to the right, and as I assign rotation, 1 to 2 to 3, I see that it's a counterclockwise rotation. My lowest priority group is backwards, which means I'm observing this from the correct perspective. So limonene here has an S chiral center. Okay, some good practice on absolute configurations. If you have chiral centers in your molecule for your analysis assignment, I encourage you to go in there and assign absolute configuration, or come back to these molecules up above and ask yourself how you can assign R and S to chiral centers up here. Now, I want to talk about chiral molecules. There's a fairly easy way to represent whether a molecule is chiral. Chiral molecules must lack symmetry, which means that they have at least one chiral center. Some molecules have exactly 0 chiral centers, which means that we can only describe them as achiral. But there are some molecules that are technically achiral because they have a plane of symmetry despite having chiral centers. These we call meso compounds. These have at least 2 chiral centers. And they have at least one plane of symmetry. So technically the definition of a chiral molecule is not having 0 chiral centers. The definition is having at least one plane of symmetry. But compounds that are strictly achiral also lack chiral centers. Compounds that are achiral by way of meso have at least 2 chiral centers, and those 2 chiral centers are reflected into each other. So as we look at these molecules given, and we can even flip back to the front page and analyze these original compounds, we look to see whether they are chiral or achiral. Acetaminophen had 0 chiral carbons, achiral, no other descriptor for it. Ibuprofen had 1 chiral carbon, chiral, no other description for that molecule. Threonine had 2 chiral centers, but there is no way that these chiral centers can reflect into each other. There's no way that these can have a plane of symmetry that relates them as mirror images. That's because one of the chiral carbons has a methyl and a hydroxyl group. The other chiral carbon has an amine and a carboxylic acid group. Those groups are never going to be symmetric. So despite having 2 chiral centers, it does not have a plane of symmetry, which means it has at least 1 chiral center and no plane of symmetry. Threonine is strictly a chiral molecule. Go through these other compounds and see if you can find planes of symmetry, see if you can identify chiral carbons, And if not, then label them as chiral molecules. The same for methamphetamine, isocitric acid, ascorbic acid, and limonene. See if you can find whether these are chiral or achiral. As we go back to the backside, I want to distinguish this idea from this idea of molecular descriptors, describing them as chiral, achiral, or meso, from the idea of molecular relationships. That is, any one molecule can be chiral, achiral, or achiral meso. But you need at least two molecules to have a relationship between them. Take, for example, the idea that pentane and 2-methylbutane are structural isomers. I can't look at one and describe it as a structural isomer, but by having two, I can relate them as a structural isomer. The first structural isomer, the first molecular relationship that I want to talk about is the enantiomer pair. Your hands are enantiomers. They are mirror images, perfectly identical in every single way, except that they are opposite to each other and cannot be superimposed. Enantiomers are considered non-superimposable mirror images. And that is a lot of jargon. So an easier way to identify that is to say that every chiral carbon, every R or S, is different between the two. Every R or S is swapped. In the example of methamphetamine, where one is highly addictive and the other is the active ingredient in Vicks Vapor Rub, these are an enantiomer pair. These are enantiomers to each other. They are mirror images, and as you can see, I can slide them over and get their bond lines to perfectly line up, much like I can with my hands. But their orientation in space of the chiral carbon is exactly opposite, much like my fingernails when my hands are superimposed. These are enantiomers, and we have already identified that the chiral center has swapped between R and S. Every chiral carbon has swapped. There's a relationship that we get from enantiomers too. When we have a 50-50 mix of enantiomers, we call this a racemic mixture. This actually comes back to a compound called racemic acid, which is a chiral compound. And racemic acid forms in 50-50 mixtures often. And this was the first evidence of chirality in molecules. So a 50-50 mixture of racemic acid, R and S, came to be known as a racemic mixture. Racemic acid was then rebranded and was given a new name, but the term racemic mixture stuck to describe this 50-50 mixture of enantiomers. An application of that. If you were to produce methamphetamine for the purposes of your Vicks Vapor Rub, you would not want to have a 50-50 mixture because your patients would be getting addicted to half of the solution that they're putting into their bodies. You need to make sure that you have a pure, we call that enantioselective or enantiopure solution. An enantiopure solution would be the version of methamphetamine that will not get you hooked to it. The other relationship that we're going to discuss is diastereomers. Say that with me. Diastereomers. You hear stereomer, which is telling you that these are stereoisomer relationships. But this term dia, what I like to think of is that there are two facets for you to recognize. Now, diastereomers are also non-superimposable, non-mirror images. They are not exactly the same, but exactly opposite. They have more than one thing different, but at least one thing the same. So the way that I look to identify diastereomers in a relationship is at least one chiral center stays the same. That's at least one R or S in common, and at least one chiral center is flipped. Oops. That is, one R has become S, or one S has become R. There's a cool connection that molecular relationships have to molecular descriptors. All chiral molecules have enantiomers. No meso compound has enantiomers. Meso compounds have a plane of symmetry, which means that they cannot be non-superimposable with their mirror image. They are always superimposable with their mirror image. Not all chiral molecules have diastereomers. Take, for example, methamphetamine. One chiral carbon. If that chiral carbon changes its configuration, it is now the mirror image because all chiral carbons have swapped. So I cannot have this dual relationship of one chiral center the same, one chiral center different. Not all chiral molecules have diastereomers, but all meso compounds, because they have those two chiral centers, all meso compounds have at least two chiral centers, at least two diastereomers. No enantiomer, at least two diastereomers. Always an enantiomer, sometimes diastereomers, depending. Strictly achiral molecules can also have diastereomers. I'll give you an example of that. But typically achiral molecules have no stereoisomerism. Achiral molecules typically don't have any enantiomer or diastereomer. I want to look up here at Lawson first. Decide whether Lawson is described as chiral, achiral, or meso. There's only one position in this molecule that is an sp3 hybridized carbon, and that is a CH2 group, which means that there are 0 chiral centers. So this compound, Lawson, is an achiral molecule. The relationship we see between these two structures, they are identical. The only difference is that one has been flipped like a pancake. They are mirror images. Everything has a mirror image. But these are superimposable, not non-superimposable. These are superimposable with their mirror image. Take one and flip it over, it perfectly superimposes. When we look at oxycodone, oxycodone is a chiral molecule. We see chiral centers in more than one place, and there is absolutely no symmetry between those chiral centers. So there is not the possibility that there could be a plane of symmetry making it a meso compound. When we look at this structure to the right, we find that the hydrogen goes from wedged to dashed. This quaternary carbon goes from a wedged bond to a dashed bond. The tertiary alcohol goes from wedged to dashed, and the bond to the tertiary amine goes from wedged to dashed. Sorry, every R or S is swapped. Every chiral carbon has swapped. These are related as enantiomers. And if they're present 50-50, that's a racemic mixture. If they're present 90-10, then there's an enantio excess of one or the other. Let's look at bisphenol A glycidyl dimethyl acrylate. Now this may look like a very large molecule, but there's not a lot going on inside of it. As I analyze from left to right, I come across a chiral carbon at that secondary alcohol, and then I come through across the rings back to a chiral carbon at the other secondary alcohol. Two chiral carbons that seem to be symmetric to each other. This portion in the middle of the molecule, the quaternary carbon, is perfectly identical left side and right side. And because my OH group is wedged and wedged, these chiral carbons are symmetric to each other. I could cover up half of this molecule, redraw the other half based on what I see, and I would get exactly what I have. Those are mirror images, which means that this is a meso compound. What I have beneath it looks to be the mirror image of my structure. The top half has reflected to the bottom half. Every bond has swapped two groups. If it's the mirror image, then we might be compelled to think it's the enantiomer of the compound on the top. But remember that meso compounds have no enantiomer. They are superimposable with their mirror image. So there's two ways to think about this. If I take this bottom molecule and I flip it over like a pancake, I'll get my entire carbon chains to line up perfectly, but the wedged OHs on top will now be trying to superimpose with dashed OHs on the bottom. That doesn't seem to superimpose. In fact, that seems to give us the same relationship that the amines did before. They come over, the bond lines overlap, but the groups don't line up. Well, let's not flip it then. Let's take this bottom compound and let's spin it around. Because both sides are symmetric to each other, I can spin these alkenes, spin these esters, spin these ethers. I can spin them around completely and get them to line up with their opposite side without flipping the wedged OHs to become dashed OHs. Because this is a meso compound, these two structures are identical to each other. I want to pause here, and I want to talk to you about a diastereomer of this compound. To show you a diastereomer, what I'm going to ask you to believe is that I swap one of these groups from wedged to dashed. I keep one of the OHs wedged, I keep one of the OHs dashed, and then we have our normal compound below where they were both wedged. These are no longer mirror images. I have a wedged OH that is a mirror image to my wedged OH, but now I have a dashed OH, which is not a mirror image to a wedged OH. This is groups pointing in opposite directions. These are not symmetric. These are non-mirror images. Now, when I spin this around again to try and get them to superimpose, this wedged OH is going to spin around and sit above the plane of the dashed OH. One group goes down, one group goes up. In the idea with my hands, one has nails pointing down, one has nails pointing up. Non-superimposable, non-mirror images. These are diastereomers. And we can analyze, this is an R absolute configuration. This is also an R absolute configuration. This is an S absolute configuration, and this is an R absolute configuration. Remember our rule that for diastereomers, one chiral carbon must stay the same, one chiral carbon must be different. In one compound, I have RR. In the other compound, I have RS. These are not the same molecule. They are not mirror images. They are diastereomers. Let's come back to this compound here. Decide whether the compounds are chiral, achiral, or meso, then decide what the relationship is between the two compounds. This compound does have more than one chiral center. It has 3. But there is no plane of symmetry, so these are chiral molecules. I notice that one chiral center preserves its configuration. The wedged methyl stays wedged. But 2 chiral centers change their configuration. One thing stays the same, more than one thing changes. These are also related as diastereomers. Now I want you to take a second to try and label the configuration of the chiral carbons on the left, and I want to show you how we can communicate which stereoisomer we're looking at by naming the compound with its absolute configuration. So find the absolute configuration for these 3 chiral centers. I'll start with the carbon on the bottom. I'm going to use this so I have a little bit more clarity. On the bottom, my highest priority is easy. It's bromine. My second highest priority is the carbon connected to bromine as opposed to the carbon not connected to bromine. And my fourth priority is the hydrogen coming towards me, which means as I assign this 1 to 2 to 3, it appears to be counterclockwise. I'm looking at it wrong. That is an R absolute configuration. I'll do the same thing for the carbon on top. Bromine takes highest priority. Carbon connected to bromine is second. Carbon not connected to bromine is third. And this time my hydrogen is dashed. So when I assign 1 to 2 to 3, it is what it appears. It's an R absolute center. Okay, this got a little crowded, so I'm going to analyze the absolute configuration of that top carbon on the right. The reason I'm doing that is it preserved its absolute configuration. It has not changed, so I can analyze it on either compound. As I look at my groups, the first priority, the easiest priority to assign is the hydrogen that is dashed. Other than that, I have carbon, carbon, and carbon. Now I have a secondary alkyl halide carbon, a secondary alkane, and a primary alkane. Remember there was a tip earlier on how to assign absolute configurations with these carbons. The higher the degree of substitution, the higher the priority. That means primary is going to have more hydrogens than secondary. Secondary will have more carbons. So primary is going to lose out in this race against carbons. As I compare secondary alkane to secondary alkyl halide, the alkyl halide has a halogen attached. That's a higher priority group compared to just another carbon. So now I have my absolute configuration at the top, also R. I'm sorry, this was not intentional. By the way, that is for this compound on the left, we have R, R, and R. The compound on the right, given the fact that two chiral centers have changed, can you label the absolute configuration of these other two carbons without doing any work? Yes. This blue R alkyl halide has swapped the position of its hydrogen and its bromine and is now an S chiral carbon. And this R red chiral carbon has swapped two of its groups and is now an S chiral carbon as well. So here's how we distinguish these by putting these in the name. First, identify the parent chain. Cyclohex. The suffix, because there are no alkenes, no alkynes, no alcohols, is hexane, cyclohexane. My substituents, bromine, bromine, and methyl. My locant set, 1, 2, 3, or 1, 2, 3. I can have my lowest locant set in two different directions, be 1, 2, 3. Well, how do I decide the lowest locant set if there's a tie between the two? The tie goes alphabetical. Halogens are not higher priority than methyl, but they are first alphabetically in a tie. So this is going to be position 1, 2, and 3, which gives me 1, 2 dibromo, 3 methyl, cyclohexane, all one word. But I want to describe the chirality of this diastereomer. I don't want to describe the chirality of this diastereomer. I can't use words like cis and trans because this is a tri-substituted compound, not a di-substituted compound. I have to be able to communicate every chiral center explicitly. So we list these carbons. All of them are R. And in the front, we'll say chiral carbon 1 is R, chiral carbon 2 is R, chiral carbon 3 is R. 1R, 2R, 3R, 1, 2 dibromo, 3 methyl cyclohexane. We have now communicated in its nomenclature everything about its structural configuration and absolute chiral configuration. Okay, I told you earlier that I wanted to give you an example of an achiral molecule that has a diastereomer. If we look at the compound, (1,4) cyclohexane diol, we can draw this as cis 1,4 cyclohexane diol or trans 1,4 cyclohexane diol. This compound, both compounds, are achiral. They have at least a plane of symmetry running through the carbons 1 and 4. Chiral compounds do not have planes of symmetry. These carbons that have the alcohols attached are not chiral centers. They're attached to CH2, CH2, and then the opposite side of the ring, identical to each other. No chiral carbons, at least of plane of symmetry, and yet these two compounds are not superimposable. They are not mirror images. They are non-superimposable diastereomers. With these other two compounds, geosmin and penicillin, geosmin is the compound responsible for that smell of rain. Humans are very sensitive to geosmin. What I wanted you to do was draw both the enantiomer of this compound and at least one diastereomer for this compound. The enantiomer is easy. Every chiral carbon, as shown, has a flipped wedge or dash. That's now its mirror image. Or the entire molecule, as shown, is drawn opposite from left to right. That is also its mirror image. What is the relationship between these two compounds? Well, if the compound on the right is the enantiomer of geosmin, and the compound on the left is the enantiomer of geosmin, then these two compounds are identical to each other. If I take the compound on the left and I flip it like a pancake, these wedged groups on top become dashed, and this dashed group on bottom becomes wedged. There are a lot of diastereomers that can be drawn here. You can keep any two of the positions the same and change the orientation, the configuration of one carbon. Keep one carbon the same and change the configuration of any other two. In fact, to calculate how many stereoisomers exist, we can use a quick calculation. Stereoisomers equals 2 to the n, where n equals stereocenters. That includes chiral carbons. It's not limited to chiral carbons, and we're going to talk about more stereocenters later in the semester. But in this case, I have 3 stereocenters, so geosmin has 2 to the 3 stereoisomers. 2 times 2 is 4, times 2 is 8. 2 cubed gives me 8 different, unique stereoisomers of geosmin. One thing that you have to do here is subtract 1, let's say 1 times y, where y equals mesoforms. For any mesoform of your compound, you do not have its enantiomer, so you will have 1 less stereoisomer. If we look at this bisphenol A glycetyl dimethyl acrylate, we recognize that there were 2 chiral centers, so that's 2 to the 2, which would make me expect 4 stereoisomers. But I have 1 where both groups are wedged, and 1 where both groups are dashed that are the same exact compound. Then I have the group on the left wedged and the one on the right dashed, the one on the right wedged, the one on the left dashed. So both wedged or dashed, 1 wedged, 1 dashed on the left, 1 wedged, 1 dashed on the right. So this is 2 to the 2 minus 1, because there is a mesoform, which does not have its enantiomer. I don't have you do a lot of calculations with these, but I do want you to be able to recognize that. So to wrap up everything on this worksheet, can you assign the absolute configurations to the chiral carbons in penicillin? And once you have, can you draw the enantiomer to penicillin? Priority 1, priority 2, priority 3. That's 1, 1, 2, 3 appears counterclockwise. Priority 4 is going away. That's an S absolute configuration. Here, priority 1, priority 2, priority 3 Priority 4 is going away. 1 to 2 to 3. It's clockwise. That's an R configuration. And here, 1 to 2 to 3. Notice how sulfur is a higher atomic mass here than oxygen. In noticing that, I screwed up earlier. I labeled this S configuration as 1 because of the nitrogen, 2 because of the carbon to oxygen, and 3 because of the carbon to nitrogen. But actually carbon to sulfur, sulfur is a higher priority than carbon to oxygen, the oxygen. So this is actually 1 to 2 to 3, which is clockwise, which is R. R, R. Here we go again. Nitrogen is 1. Carbon to oxygen is not higher than carbon to sulfur. Sulfur wins. 1, 2, 3. But notice that my fourth priority group, hydrogen, is going backwards. So 1 to 2 to 3 appears to be R, is actually S. To draw its enantiomer, all of my chiral carbons swap places. I didn't mean swap places, swap configurations. Or I draw my molecule opposite from left to right. These appear to be two different structures, but they are actually the same molecule flipped over like a pancake, just like we did up here by drawing the enantiomer of geosmin two different ways. Okay. We have covered chirality in the sense of chiral carbons and their absolute configurations, chiral molecules, and their relationship to other molecules. Keep studying. Good luck on your unit test. Happy studying.